All right, continuing on. So we talked about bubble sort, selection sort, and insertion sort. And quick recap, what did we learn about those?
Selection source.
For
No, for linked list. Right? No, insertion source.
An array.
For an array. Yeah, selection sort is probably your best bet for an array. Although you can do it for a linked list, it's just far more complicated.
Oh yeah, that's right.
A lot of pointers jumping around, but it's still possible. It's not impossible, it's just annoying. Insertion sort, on the other hand, is probably a lot better for a linked list. And then what was the one advantage of bubble sort? Easy to code, right. Right. And don't forget that. That's actually an important characteristic. All right. But of course, there are better sorting algorithms than those two. All right, they're going to go talk about, wow, comparison tree. We're going to just totally map this out. Y'all haven't taken discrete math, so I cannot go into this too much. But the basic point of this comparison, wow. The point of this comparison is that if you have n elements and you sort it by comparison, then the best you can ever do for sorting is n log n. And n log n is significantly faster than n squared, and all our previous algorithms have been n squared on comparisons, so we should be able to come up with a better algorithm than the previous three. So first off, quicksort uses divide and conquer technique. So the list is partitioned to two sublists, and then it sorts each sublist. Okay? Sorted sublists are then combined into one list in such a way that the combined list is sorted. All the sorting work occurs during the partitioning of the list. Interesting. All right. So you cut it in half, and then you sort. Actually, what does this sound like? Let's start there. You cut the list in half, and then you call qsort. Binary search. Not a binary search. You got the binary. It's
Binary tree.
Right. We haven't gotten to trees yet. That's next. Hang on, we'll get there. Don't worry.
Oh, wait, we'll get there. Trees.
Trust me, that's next. Usually the midterm has binary trees, but we didn't get to that. So yeah, it's next. But good start. The list is partitioned into two sublists, and then you call quicksort on the sublists. How does CS majors have a hard time with what type of algorithm is what I'm asking? Is that? Call it binary tree, divide and conquer in half. Because it's the reason I'm asking is it's not spelled out in the text up here, but it's pretty much implied. So you call quicksort given an array. You cut that array in half, and then you call quicksort on the two halves.
Binary search.
So it's similar to a binary search where you're searching down, but a binary search, it either goes one way or the other. But now we're calling quicksort on each side. But what type of algorithm was binary search is what my question is. That would be the big O analysis. So. Was it, let me put it this way, was it an iterative solution?
Recursive.
It was a recursive type algorithm. So it's better to think of it recursively. Quicksort, you can do quicksort, of course, iteratively, because anything you do recursively, you can do iteratively, but it's better to think of this as a recursive algorithm when you're thinking about quicksort. So you just cut in half, and then call quicksort on the two halves. And so then you're basically, after you cut the array in half, you quicksort each side, so you're recursing on yourself.
So,
Yes.
do you only split it in half once?
Well, if quicksort, when you call quicksort, it splits it in half and calls quicksort on the two halves. When you call quicksort again, it's going to split it in half and call it on the two halves again. Of course, that means we need to have a base case.
Eventually, you're going to get down to where you only have two things.
Right. And that's going to be pretty easy to sort, I hope. We good there? Jonah? Take a breath. You got this. All right. But if we're going to split it between a lower and an upper, we need to come up with a pivot. So a pivot is chosen to divide the two lists in this lower sublist and the upper sublist. Now this pivot needs to have a very particular property in that once you put the pivot, everything to the left of the pivot has to be less than the pivot. Everything to the right of the pivot has to be greater than the pivot. That way you have the one element that's correct, and then when you call quick sort, once those two things are sorted, you know that your array will be correct. There are many ways to choose a pivot. Ideally, you want to have the pivot divide the list into two sublists of nearly equal size. I really hope they give a picture of how this works. All right. So, let's say you have this array up here. Wow, they don't go through the steps. All right. One moment while I get this camera out. All right.
Doesn't look like there's a glare.
What's that?
Doesn't look like there's a glare today.
No glare today? Oh, that'd be great. All right. Oh, green marker. Anyone have a red marker? Oh, nice. Thank you, Jay. I went the wrong way. We'll go ahead and write these numbers up on the board. So we have 45. Good morning. 82, 25, 94, 50, 60, 78, 32, and 92. All right. Okay. And there's definitely a glare. I should get really good at this by the end of this semester. There we go.
I'm really good at boxes.
You haven't seen that type of box before?
No, I don't think so.
It's with the antenna. Aren't you used to antennas?
That's an advanced box.
Yeah. I mean,
I haven't gotten.
look, you haven't gotten to this level yet, all right, man? All right. Okay, there are many ways to choose the pivot. In this one, they chose the one in the middle, aka the 50. A good way to do this, aka like when, I don't know, you're on your exam. So you're going to have the 50, and what's going to happen is you want to move it to the center. So what numbers are less than 50? So we got 45, 25, 32. Is that it? All right. Then we'll put the 50. Circle your pivot. Then you want to write all the numbers that are greater. So 82, 94, 60, 78, 92. Okay? Now, you've split it in half. And you're going to call quicksort on each side, right? So, what do you want the pivot to be here? 25?
Yeah.
Sure. So, what numbers are less than 25 of these? None. So, 25 is right here. Circle the pivot, and then you'd have 45 and 32. Recurse on this. Let me see, eraser. We'll go in and get rid of the antenna. Only for Matt. You can choose either one to be pivot, but you'll have 32, 45. Of course, you have 25 right here. All right, so then that's been sorted. So now we want to choose a pivot here. We'll probably choose a 60 since it's in the middle. What numbers are less than 60? None. So we'll go 60, 82, 94, 78, 92. So now we got to recurse on this half. Got to choose one in the middle. Which one do you want?
78.
78, we'll choose 78 as the pivot. Again, circle it. Any numbers less than 78? No, so we got 78, 82, 94, 92. All right, so we're done here. Pivot, 94. What are less than? Well, we have 82, 92, and 94. You would recurse one more time, and then you'd be done. All right, you'll see the steps here. Okay. The way I did it up on the board is not exactly how code would necessarily do it. I just wanted to make it so pictorially you can see what is happening. All right. So after the first iteration, if you notice back up here, we have these three numbers, and with there, yeah, 32, 25, 45, 50, and then you recurse on the upper set as well. All right. So how do we do each of these steps? Can we erase this on the board? Because there's different ways to partition the array out. There's different ways to go about it. So there are different quick sort algorithms per se. They just follow the same general scheme. First, you determine the pivot, and then you swap it with the first element of the list. So I'm going to go with, this is the step in between each step. So you need to first swap it with what's in the beginning. So you have 50, 82. On the board, good. 25, 94, 45, 60, 78, 32, and 92. So your pivot's right here. Let me spell pivot correctly. Your pivot is equal to 0 because that's the index of the pivot. Let me go ahead and call pivot index for y'all. Equals 0, pointing to here. All right. Then the next step is that you want to have, for each remaining element, if the current element is less than the pivot, increment small index, and 2, swap the current element with the pivot element pointed to by small index. Swap the element pivot with the array pointing to the small index. Is it? Wow, that was kind of confusing. All right. You're going to have an you need to iterate through the array as you evaluate the whole partition, okay? All right, that's what needs to happen. So I'm just going to call it position. Of course, it starts at 1 because it's pointing at the 82. And you're going to have a lower index, which will also start at, let's see, lower index. We'll have it start at 1, and you'll have an upper index equal to 1. All right. 82 is greater than 50. What's that? Position starts at 1, your lower index starts at 1, your upper index starts at 1. 82 is greater than 50. So that just means your upper index is going to increment to 2. And then we'll go and visit the next one. 25. Position's now at 2. Your for loop inside is incrementing position. 25 is less than 50. So it's going to swap 25 with what's pointed at lower index, aka 1. So it's going to swap these two values. Okay? So it's going to swap those two. You have 25 and 82. Lower index is going to increment by 1 up to 2 because you're up here. And then upper index will also increment by 1. This one's kind of shadowing position. I'm just trying to make it clear what's happening. And then you'll increment position by another variable because you're now going to look at the next value. All right, you see what's happening? All right. 94, is it greater than or less than 50? It's greater than. So we just increment the upper index up to 4, and then position up to 4 as well. 45, is 45 less than or greater than 50? It is. So we're going to swap, is less than. So we're going to swap the 45 with what's being pointed to by the lower index, which is currently the 82. So you're going to swap the 82 and the 45. And then you're going to increment both of these, 3, 4, and 3, 5. And then you're going to increment position, which will point to the 60. All right, before I go on, let me show you what's happening here. Lower index is 3, meaning that everything between the pivot and lower index is less than the pivot. Okay? Everything going from the lower index to the upper index, 94 to 82, is greater than the pivot. So it's creating these two subsets or two arrays, subarrays, that are either less than or greater to the pivot as it moves down the array. Does everyone see that? All right, we'll continue on with how it does this. Is 60 greater than or less than 50? So what do we need to do? Yeah, that's what we got to do. $78 greater than or less than? Greater than. So we increment the upper. All right, 32 less than or greater than?
Less than.
So what do? We increment. We don't increment both first. What do we need to do first?
This is a swap.
Swap. What are we swapping?
The 32 with whatever the lower position you want.
And that one's pointing to what?
The third element. The fourth element.
Fourth element, which is the
94.
94. So we need to swap the 94 and the 32. Then we increment both. 4 and 9. Points to 9. 9 greater than, 92 greater than or less than?
Greater than.
So what do we do?
Increment the upper.
We're at the outer. And we're done because we're at the end of the array. Now that this step has completed, this is the partitioning step, the last thing we need to do is we swap what lower index is pointing to with the pivot. All right? I'm sorry, not what lower index is pointing to, sorry. One less than the lower index. One less than the lower index and the pivot. So the lower index is pointing to 82, so we're going to swap the 32 and the 50 because it's one less. So we need to do one less. Why do we need to do that? What's going to happen when we do that?
Because it's going to make sure that 50 is where it's supposed to be.
Where it's supposed to be in the array. And something else that's very important. Everything, because this isn't a selection sort, that's what selection sort would do. But more importantly, everything to the left of the 50 is less than 50, and everything to the right of 50 is greater than 50. So one less than lower index, which is 3, we swap it with the 50. Let me go ahead and erase this. And then we update the pointer, the pivot index to be, that should be 3, which was, of course, 1 less than the lower index. So pivot index 1 less than lower index, right here. There's your pivot. Everything to the left is less than 50. Everything to the right is greater than 50. All right. That's the hardest part of quicksort, by the way. It's getting this section down. Are there any questions about this partitioning method? Nothing? All right. This is where they're talking about small index greater than index until they get to the end. Okay. Okay. Let's what are they doing here? List before sorting. Okay, so they're showing you what they did here. So we're gonna go through another example through the slides. Great. 52 is what they're selecting. It's in the middle. They swap it with the 32, so 52, 32. And then, well, they're just saying somewhere in the middle, small index, 22. I kept track of what came next. 11, which is smaller, so they're going to swap it with the 96. Notice that that's what happened. The 11's here, 96 here, and they increment small index, and your other index continues on. Now, in the version I showed up on the board, I kept track of the lower index and the upper index, but if you watched, you notice that the upper index was also the position. So you don't need both of these variables. I just put them up here to make it clear what was going on. Also in their version, they're keeping track of the small index, which is the last value that is smaller. I just kept track of one after that. Either way, you can take that into account. So 58, of course, being bigger, so they just increment, they just keep on incrementing. And then if you actually look at this, they would increment 66 and 88. But what would happen when they hit the 45?
You have to swap it
With the
with the 87.
87. And that's the 87, and there's the 45. And then the last thing is they swap the small index and the pivot. Okay.
So finding out the pivot, do you usually just do like size divided by 2?
That's what I was thinking.
That is a common way to do it. Yeah. Pick the pivot any way you want. There are, when people do analysis of quicksort, they come up with lots of different ways to quickly choose a pivot, trying to determine which pivot would be the best. The trick, though, is you don't want to run through the whole array. You just want to pick something. So picking in the middle is common. Some people just pick the first one because then you don't have to swap anything, right? You don't have to do that first swap. Laziness, but you know, whatever. It works, whatever. It still works. Yeah, you still gotta, because you're gonna have to eventually swap anyway. So some people choose at the end. Other people will have a quick randomization of choosing where the pivot is to just in case your data is following some pattern. Hopefully they can try and break up that pattern, and we'll see why they do that in a moment. But that's why different quicksort algorithms will actually behave differently, because they have to choose, each can choose a pivot however they wish. All right, quicksort analysis. All right. So how long did this first step take? Basically going from, we chose the 52 to a pivot to putting 52 in the middle. How many comparisons did we do?
Compared everything.
Compared everything to
52.
52. So how many comparisons is that?
The size minus 1.
Right, so comparisons per partition equals size minus 1, aka O of n, right? N minus 1, it's O of n. Okay. Now, I wish I had my old picture up. When we go and we, on this side, how many comparisons are we doing? Because we're going to recurse on this side, choose a pivot. How many comparisons are happening here?
Size divided by 2.
That's a good guess. Roughly size divided by 2. Over here, size divided by 2. Now when we're over here and we have to, after partition, we recurse again, what's the new one? Size
Divided by 4.
4, and then after that would be size divided by 8. Okay, so it's actually going down pretty quickly. So the next question is, how many of these recursive calls do we need to do? This is where it gets hard or tricky.
It depends on how many times you have to.
Let's take the best case where the pivot is always in the middle.
Well, that doesn't have too much, right? I mean, it's all dependent on the size. Would it be size divided by 2 number of times?
No, but you're on the right track. This is hard to think about. Let's go look at let's look at this. Let's go ahead and complete this one out. Here we go. Oops. we'll take the 25 as the partition on this side. So you put the 20, and well, the 25 would be at the beginning, and then you go 32, 45, right? Then we take this one, it's in order, so 32, 45. And technically you would recurse on this one too, but you're done. All right, we're good. Over here, you probably choose a 78 as the pivot. Only 60 is less than 70, so we'll have 60, comma, 78, comma, 82, 94, and then 92. Pivot, 60, you're done. Over here, you'll probably choose a 94 again. So you'll have 94. I put the 94 on the wrong side. Probably have 82, 92, 94. And then you would recurse one more time and you'd be done. All right, so the question is, each time, if you look at this per level, at this level, how many comparisons were done?
Size minus 1.
Yeah, so O of n. Comparisons per partition. At this level, O of n. How about this level? So this plus that.
That'd be log again?
Well, up here we had size minus 1. Now we've removed one number, so it's really size minus 2. Or, let me make sure about O of n, right? Okay. How about this level right here? So this plus that. Also, there's a 60 right here. Oops. Make that a little clearer. Really, just taking the 50 out, the 78 out, and the 32 has been, 25 has been taken out. So you've taken out, I guess, roughly 4 of the numbers, right? N minus 4, which we'll say for the sake of argument is O of n. All right. Okay, but then we're basically done. So the question is, so what I'm trying to point out here is that each level, you're doing about O of n comparisons, right? How many levels are we doing? How many elements do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 3 levels. Okay, actually there's a 4th level down here, technically. But if it was 8 elements, it could have been 3 levels. I know this is hard to see. Without discrete math, it's hard to show. But you're dividing everything by 2. When you're dividing everything by 2, what big O should you jump to?
Log in.
Yeah, always jump to log n when things are being divided in half. That's the best rule of thumb for now until you take discrete math and you go into algorithms. We'll go into a better analysis of big O. But whenever you hear someone say divide by 2, and that's what's happening all the time, we're dividing into 2 partitions, just think log of n is going to be in here somewhere. So your number of comparisons per level is O of n, and how many levels do you have? O of log of n. I forget the exact analysis, but then you multiply log of n times O of n, and now you have n log n. So total comparisons is O of n times log of n. See if the slides confirm. Average case, it's actually really complicated for quicksort to get this out, but it's n log n. And worst case is n squared. How can it be, what's worst case? Ooh.
You assign every time.
You have to,
Assign every time. Every time you check. Just one.
No. No, if you're swapping, it could still be n log n. Let's look at the board. What would be the worst case scenario for this algorithm?
You start with n squared. It said n squared divided by 2.
I'm sorry?
No, I was reading that.
Okay. What would be the worst case situation for this algorithm?
All the numbers are the same.
All the numbers are the same.
Actually, no, that wouldn't matter.
That wouldn't matter too much.
I thought about it.
What would happen if the pivot was always the lowest number?
So it would be greater and you'd have to, kind of a mess, right?
If the pivot was always the lowest number, then you're moving that number to the beginning. And then when you recurse, have you really divided it in half? What have you done? So what's your algorithm now? It's like,
It's squared.
it's n squared, correct. But what algorithm has your quick sort deteriorated to? Which n squared sorting algorithm? You find the pivot's always the lowest, so you move it to the lowest position, which is selection sort. So quick sort can deteriorate to selection sort in the worst case. So since selection or quick sort can deteriorate to selection sort, then it can become n squared in the worst case. In practice, that rarely happens. So we usually are okay with the average case being n log n. And yeah, we're done. All right. Good. Any other questions about quick sort? All right, so let's go ahead and